We've been talking about relations. And we've been talking about special types of relations called functions. We can also group relations by other words. Like, for example, you can probably figure out half this lesson if I ask you this question. Which one of these two graphs would you think is a linear relation? Which one would you think is a linear relation? Linear. Linear. Why? Yeah, because it forms a line. Okay, that's the whole meaning of linear, means it forms a line. This we would call a nonlinear relation because it has a curve. Okay, and I forgot to, am I recording? I am recording, I just don't have my. Anyway, so what's a linear relation? Linear relation is a relation that forms a line in a graph. Now, a linear relation doesn't necessarily have to be a line, but it can form a line. Like this one is technically not a line. It's a segment because it has a starting and stopping point. But it forms part of a line. That would go like that. Same with like a series of points. If I had a series of points that look like this, well, technically it's not a line, but it forms a line, which means a set of points could be a linear relation as well. Okay? So let's look at this example. And we'll keep the numbers pretty simple. Pizza place charges $5 for an individual sized pizza plus 75 cents for every additional topping. Okay, so this is an example of a relation because it's a relation between the cost of the pizza and the number of toppings. Okay, independent variable is the number of toppings. Dependent variable is the cost of the pizza. And remember, there's different ways we can show relations. Table of values, graph, equation, which we'll talk about later on in this lesson, arrow diagram, which we won't use that much in part. Okay, so let's look at a table. We need to come up with some numbers to graph. How much does the pizza cost if it's just, assume that no toppings means just cheese? $5. One topping. $5.75. $2. Two toppings. $6.50. Three toppings. $7.25. Where are those math money skills from middle school? Four toppings. $8. Okay, we can graph it. I'm not sure why. I forgot to put in the. So if there's 0 toppings, well, let's see. The scale for the vertical is every grid line is $1. So that would be 0.5. For one topping, it would be $5.75. Well, I have to get approximate here. So it would be under 6, but close to 6. For 2 toppings, it would be about halfway between 6 and 7. So about there. 3 toppings would be $7.25, or about there. And 4 toppings would be exactly $8. That is watch. So here's a table describing this relation. Here's a graph describing this relation. Would you call it linear? Yes, because these dots form a line. So by looking at the graph, you can tell me whether it's linear or not. Another quick question, and we did questions like this last year. Should I go like this, or should I leave the dots separated and put like an arrow at the end? Or should I go like this? Think of the question, or think of the situation. It's the number of toppings, right? Can I have half a topping? No. Can I have 1.5? No. I can only have 0, 1, 2, 3, 4. So you do not connect. But you put an arrow on the end just to show that it can go on forever until I guess you run out of toppings to put on. There's only so many toppings you can put on an individual sized pizza. So therefore, we would not know because you can't have part of a topping. It's only 0 or 1 or 2, etc. And we've already talked about how to tell if a relation is linear by looking at the graph. We've already talked about this. Okay? If points or segment form a line. That's how we can tell. Right? So we know this one above because we could draw a line through all the points and hit all the points. But how could you tell just by looking at a table? Like, what if we didn't have the graph? What if we didn't have this, but we only had this?
You would see the cost of each topping and then you just see them.
Right. Notice what's happening here. Every time I add one topping, so I add a constant amount of 1, the range value, or y value, goes up by 0.75. All the time. If that doesn't happen, it's not linear. These they don't have to go up by the same amounts. Each one though has to go up by a constant amount. So in this one, every time we go up one topping, we go up in cost 75 cents. So to explain that, okay, if a constant change in the, and we could say in the independent variable, we could call it domain values. So I'm going to call it domain values. Causes a constant change in the range values. It is linear. So therefore, this one, by looking at the table and the graph, we can see that it's linear. Okay? Now we're going to skip the second page because that's going to go back to that. I would like to go here. I would like to leave in examples 1 to 3. Okay. Here you are given two relations in table form. You are asked, now obviously there are relations. This has a relationship between temperature measurements in Celsius and Fahrenheit. This has a relationship between amps and watts. Okay. So, well, I suppose you could graph them and then see whether it forms a line. But I think it's easier just to look at the table. Is this first one linear? What are the domain values going up by every time? 5. And it's constant. 5, 5, 5. So it's plus 5. So I know that that's part of being linear, but as that one goes up by constant, so does the other variable. Does it? How does it go up by to get from 32 to 41? 9, and then 9, and then 9. So linear. This next one, well, we can see for the amps, it's also going up by 5 every time. But look at the watts, the power. It goes up by how much? And then 325. Stop. It's not going up by the same amount. This is plus 75. Now all of a sudden it goes up by something different. I don't have to go any further. It's not linear. It can't be. Okay. So that's telling if a relation given in table format is linear. Now we're going to do a little bit of graphing. And we're actually going to graph this one last. That one you may tell looks a little different than the other two, or the other three. So, first one. And I'm just going to do this. This. Well, somebody should be able to tell me how to graph this one pretty quickly. How would you graph it? Y-intercept is 2. Slope is -3, but as rise over run, it's -3 over 1. So plot the y-intercept. And then from the y-intercept, I'm told to go down 3 into the right 1. There's my line. Oh, well, obviously I said line. Which means you should be able to tell me whether it's linear or not. Yes. So this is linear. We'll save, like I said, we'll save number 2. We'll put number 3 down here. So number 3 is it the one where it's y equals? Yeah, y equals 4. I need XY axes. What would that graph look like? You should know how. Yep, horizontal line. So find a point on the grid where y is 4. There's one. And it's horizontal line. It goes through. Remember, don't just plot one point, which is what some of you have been doing. Y equals 4 is a line in which this point is just one of the points. Linear? Yep. Fourth one. X equals 1. That one. Vertical. So go on the x-axis, find 1, draw a vertical line through it. And you've got it. Linear? Yep. Okay, let's go back up to this one. What looks so different about this one? Play a little Sesame Street. One of these things is not like the other. What's different about this one? It's got what? It's got square. What is, yeah, I know, right? You're looking at it like, what? Well, let's see. Right now, we don't have any short method to graph it. You will, but not yet. Next year. We're going to be graphing plenty of these next year. But I want to show you what it looks like right now. So we're going to do a table of values. And I'm going to give you the numbers. If I told you that x was -2, what would y be? Positive 4. Because -2 squared is positive 4. If I told you that x was -1, what's y? 1. If I told you that x was 0, what's y? 0. If I told you that x was 1, 1 again. And if I told you that x was 2, 4. That should be enough to show you what the graph is going to look like. We had to do a few points. Otherwise, it would have been hard to see. So let's plot these points. So -2, 4 is up here. -1, 1 is here. 0, 0 is at the intersection of the axes. 1, 1 is here. And 2, 4 is here. Almost looks like a V, but not quite. It's got a little bit of a curve to it on either side. It's almost halfway between a V and a U. Well, you should be able to tell me whether it's linear or not. No, not linear. Like I said, this year, I want you guys to know how to graph lines in and out. Next year, you guys will learn how to graph these things inside and out. It has a special name. So as a preview for grade 11, the name of this shape is that. And it's not pronounced parabola, parabola. It's fun to say. Okay. Last example I want to look at, and I'm going to take you back to middle school. You remember in middle school, we did all sorts of stuff with percent. We haven't looked at percents at all, I think, in senior school. Not at all. So here, we are given the relation in words, and we have to figure out whether it's linear. You purchase a new car for $24,000. Every year, the car value of the car decreases by 15%. The value of the car is related to time. So I want to see if it's going down in a linear fashion. Does it go down the same amount every year? So let's find how much the car is worth after 1 year. It goes down by 15% to 24,000. How do I calculate that? Yeah, 24,000 times, 24,000 times 0.15, which gives us, I need some help here. 3,600. How much is the car worth now after 1 year? How would you find that? 24,000. So that means that the value of the car after 1 year is $20,400. And remember, new, it's $24,000. But let's keep track of it. After 0 years, it's that. For 1 year, it's that. It went down 3,600. So every time I add a year, it goes down by 3,600. That means that if I do the next year, shouldn't this go down by 3,600 again? Let's see if it actually does. So after 2 years, remember, the value of the car now is this. How do I find 15% of 20,400? Times 20,400 by 0.15. That gets you $3,060. Is it linear? It went down 3,600 after the first year. Did it go down 3,600 after the second year? No, it went down a different amount. Stop. Not linear. Okay. I don't even have to find the value of the car after 2 years. All I really need to do is look at these. It goes down 3,600 from year 0 to 1. It goes down 3,060 from year 1 to year 2. That's not constant. Okay. So just by looking at those values alone. And the last example we're going to look at for today is another relation that we're asked if it's linear. For a service call, an electrician charges $75 flat rate. So before they even do any work, you're charged $75 just for them coming out. And then when they get there, they're charging $50 an hour. So if they come and work for an hour, how much do you pay?
75 plus 50.
Right, 125. Okay. 2 hours, you pay 75 plus 50 plus 50. Okay. So let's sort of keep tabs of that. 1 hour is 75 plus 50. 2 hours is 75 plus 50 plus another 50 for the second hour. 3 hours is 75 plus 3 of these 50s. Is it linear? How much is it going up by every hour? Yep, up by 50. So every time it goes up by 1 hour, the cost goes up by $50. That's the very definition of linear. Okay. Cost goes up $50 for every hour. Okay, so what we've done is we've seen what a linear relation is, how to tell if a relation is linear or not. And the next thing that will finish this lesson is going to be how can we use these linear relations to help us answer questions, and we're going to learn a couple of new sort of terms, but we'll worry about that next lesson.